Hello everybody. Today we explain is maybe a little bit longer videos entire process of how those large semiconductor chips are designed, the design process. First of all, what we start is like architecture. Architecture depends on what you're going to design, like a CPU. Then it has an instruction set, and that's going to be the target CPU for communication, 5G, 6G, whatever. This is going to be the target, and this is the custom microcontroller unit, MCU. This instruction set is like the Risc-V or other CPU. There are many instruction set. Those are available, right? Now from there, depend on the purpose of CPU. It's go for speed, it's go for versatility, or it's go for low power. You have to make an architect. This architecture is like where you put the ALU and what kind of ALU you put, and the register set, how many register, and memory controller and instruction decoder. Those are architect level design, and this need to be done by experienced the chip designer, architect designers. Architecture is the most important things to determine the performance of the CPU. If the chip, the objective is met or not, depend on the architect. And when architect is done, then you do logic design. And logic design, I already said in the previous video, everything can be designed with the logic component NOR or NAND. Everything. Okay, there are many consideration needed, like a fan out, a fan in, and other stuff. The susceptibility of noise from the power supply and those things. There are many things, but at logic level, you look at function level. This is everything for logic design, but in practice, this doesn't make sense to design the same thing over and over, like a latch or flip-flop or multiplexer or many logic element, ALU, other, right? Other. So those logic element is created, optimum design of each logic element is created as a library. Okay, the library has so many logic component, and this library is guaranteed by the chip processing company that they are tested and works. Every logic element you use from here already tested and works. Okay, so once you have this, then your logic diagram is a very complicated logic diagram. Very complicated logic diagram made of this logic component. So you use the EDS, electronic design system. You pull out library and put together and make the logic diagram, entire diagram of the chip. Okay, and of course, if you like, your preference, you can use logic equation like a Q equals A, B over whatever, and program convert it into the logic diagram, whatever, the optimized logic diagram. And this is very important tool for the random logic, like instructions decoder and stuff. Data path, usually this is not a good way because you have to look at the timing of the data flow. Each stage of data flow, you have to look at the timing. So usually you look at this one and think about timing. And of course there is a tool, EDS tool, to check critical path. What is a critical path is from flip-flop to flip-flop. There are many logic going through, and which path is the slowest, and that determines the clock speed. So the slowest logic path is called critical path, and nowadays software is going to determine which one. Then you go back and look at, see if you can improve the design to reduce this so the clock can be faster. So this kind of a lot of logic design activity is done by logic designer. Okay, so in a chip, semiconductor chip design, there is an architect. Architect usually work with specification. This is a chip specification. What kind of instruction set in CPU, and architect. This is chip architect. And you cannot be architect unless at least minimum 5 years of logic design. You understand the logic design, and additional years of study, comparison, analysis, kind of things. And this job is a logic designer. Okay. Now, when logic design done, what's happened is the EDS software, pretty much automatic, do the placement and interconnection. So there are two things EDS does pretty much automatically. Placement means on the chip you put all this library component you use, where you create, you do optimal placement. It's how do you determine optimum? Well, depend on where you put. If this module interact with this, you put close, right? So the interconnection can be minimum. You don't put this and this far away. There's so many wire going back and forth. And placement and interconnection. Interconnection may be multiple aluminum conduction layer. Okay, and between the aluminum conduction there will be oxide silicon for insulator. So once this is created, if software causes error, then maybe you have to work on the error because maybe it's run out of silicon real space. Then you have to increase the silicon chip size, and maybe error is one wire is driving so many gates and the fan out violation, then you have to replace this kind of things, and you have to think about how to distribute the power, optimal power distribution. Okay, so there are many things you have to consider at the physical layout side, but the placement and the interconnection is going to be automatically done from based on logic design file. Okay, now once physical design is done, then what you do is generate process layer. It's a mask, and mask for each one, like you need, if you put the transistor here, it's a cross section is going to be, it's a bipolar transistor, the collector, and this is a p-type and n-type. Those are construction, you need a multiple mask. Okay, this is called the standard cell design approach, because you have a library, standard cells in the library. There is another process called the gate array. This is a semi-custom. Why this is semi-custom? Well, standard cell is a full custom. You use all the library component and put them as needed anywhere you want, and create a brand new silicon. Brand new silicon chip. The semi-custom is a gate array. You have already certain number of transistor created on the silicon already. So what you do is you hope this logical design can be all realized by interconnection only. And of course, this has this interconnection to make a flip-flop, interconnection to make a latch, interconnection to make a the multiplexer, whatever. Those are in the library. The library in this case is interconnection library. So what you do is placement, you don't need it, and generating mask other than interconnection is not needed. It's silicon chip already made, and there are certain number of gates you can use. So you estimate if logical design using like 100,000 gates. Gate is like a NAND or NOR. Then you pick correct gate array chip, which has like more than 100,000 gates on the silicon already. Then you run this logical design files, generate interconnection files, and you interconnect it, then it's done. So it's the time saving method. It's already silicon is half done and waiting for interconnection only. So as you see, since this transistor's locations are all fixed, you have to interconnect. Interconnection tend to be longer, so it's slower. Okay. And field programmable gate array is, you don't need even interconnection mask. What they do is you have a lot of transistor already, array of transistor, and the possible interconnection is made all over, and there is a fuse all over, and based on interconnection requirement, the fuse is cut and realize this gate arrays. So that's called field programmable gate array. Okay, and nowadays this become more the time saving and the cost performance is better, because this one you still need to generate interconnection mask and go through the wafer process. The last portion, the metal layer process. This can be done at your desk, right? You have a field programmer, you put chip on it, and you give the file, logic file you want to create. Then 30 minutes later, it's cut all the fuse and the interconnection done correctly. Then chip is done. So the tremendous time saving and cost saving. Okay, so that's why this become much more popular than just a traditional gate array. But this can be done, even CPU can be made nowadays, because chips number of gate array size get bigger. It can accommodate all the logic necessary for even Risc-V, Risc-V, yeah. So some company make this one using this, but the clock size you cannot expect going to the gig. It's probably 200 megahertz, somewhere around. Clock size tend to be very slow because you're compromising optimization of the interconnect and placement optimization. So it's not really optimized chip, but you can still have functional chip, and its purpose is to have a functional chip for some kind of control. I want to use Risc-V for control something. It's not really necessary that speed. I'm not doing a Risc-V for scientific calculation or time critical encoding, communication encoding, decoding. Okay, then if you're not doing that, this method is cheaper and quicker, right? So entire logic design can be even logic equation, like a program, like language, the programming like language to describe this, and run it's generate the interconnection file and burn the chip. Here you go. You can make a. This is like a even not a semi-custom. It's only custom is what you burn the fuse on the silicon chip. So this is kind of method existing right now. But when you make a high performance, you have to do standard cell approach. So far what you need is architect and logic design, and this can be more programming language, but it's not like a programming. You need a lot of experience in logic design to understand what's going on. So it's more like a hardware engineer. Well, this is the full logic design. And this is necessary when you adapted a new technology, like it's not just NOR or NAND. There is some component which didn't act like this one. There are many, and also when you mix analog. So this is by CMOS design. You cannot finish with this one. This a lot of actual hardware design, hardware knowledge and logic design is needed. So it's still very diverse. When you say logic design, what kind of logic design you're doing? Like CPU, Risc-V can be pretty much done by this method. If you are not pursuing for the performance, the full logic design is various things cannot be handled by software, automatic software design, EDS, and the performance is one of the highest clock you want to achieve. So now, once a semiconductor chip is made, the remaining job is going to be board level hardware design and software engineer. Okay. And board level hardware design, it's evolving. Nowadays, it's not like a PCB and put the chip and do the interconnection. And this is like a interconnection design and automatically generated this interconnection files and make a PCB board. But this day, high performance, like a cell phone, they use silicon chip to interconnect CPU, memory, those. So the size become like 100 times smaller. PCB used to be PCB. It's become 100 times smaller because it's silicon chip. And what you do is in silicon, you flip the chip upside down and the interconnection has a bump. And chip-to-chip interconnection is done on the silicon using like 38 nanometer. So this is like a performance enhancer, and that's what they found out when they opened and examined the Huawei's new cell phone. They use this kind of chip, and the advantage is distance becomes so small between cache memory and the CPU, then entire operation speed up. Okay, so those are new board level hardware engineer's job. Now, that's a kind of entire story of making a silicon chip. But now we get into a little bit detail area. Detail area is, can you really make NAND, NOR, entire logic? How about latch or flip-flop? Flip-flop clock dependent. Actually, you customize, you make a cell using transistor, which is not really the logic gate. When you make a latch, like a RS latch, you have a feedback, So it's retained the logic state in here. You can do that in the same way, just control polarity change, right? And if you put the latch together, then become flip-flop, because flip-flop is basically latch 1 and latch 2. You transfer data at the clock low to high, and here clock high to low. Then the data move from here to here in one cycle of the clock. Okay, that's a flip-flop basically. Okay, so can we handle by the programming like language? The programming like language is like you have a logic equation Q1, Q2, a lot of logic equation, and you have a clock low and change to high and low, and every time clock change you update the logic. And when you have a statement like if okay, latch is disabled, then Q1 stay same. Okay, so this is the else. Q1 become a new value. So that's a latch you can express by the programming language. And if you put together, as I said, two stage, then become a flip-flop. Then clock edge triggered flip-flop become possible using programming language. So basically everything can be done in the logic design using programming language, but programming language is not efficient because each latch and flip-flop, there are a lot of flip-flop and latch inside the chip. It's all expressed like that. And actually for optimum design you have to combine, like you have architecture, this register and ALU, so and so, and each module can be programming language generated logic, but this entire connection is better controlled by logic design concept. Okay, if you describe everything by programming language like entire software, then a lot of things is lost in the code. It's an important consideration in the hardware design. So okay, so that's what it is. Okay, so now after chip is made, actually very important thing is, okay, we created a chip, say Risc-V. Does it really work? Any bug? How do you check? This is a big subject. How do you test chip? What if it's a FPG, the one there's a fuse supposed to be disconnected, but it wasn't disconnected. But this chip is so complex. You give all the instruction set, it seems to be working, but only certain type of data multiplied, then this part of the data is incorrect. This kind of bug happen right? Because inside this, you give a test pattern and check outside. Yeah, multiplication seem to be working. Yeah, how do you know? Like a 32-bit times 32-bit. You have to test 2 to the 32 times 2 to the 32 cases, all the cases. You cannot check every cases. So what you do is you pick only typical case, boundary case, and test it. But you may miss this kind of bug. Now, how do you test this? And this kind of testing is another challenge, especially when you have a lot of flip-flop inside the chip. Flip-flop logic state cannot change so easily. It's very complex condition of the logic is change. So you don't know if this particular one flip-flop is working or not by generating test pattern and run through this chip. Well, you have a million test chip, but still it doesn't hit this some special cases of logic state. So this is a hardware bug debugging. Hardware debugging is an entirely different subject than the software. Software, you can debug it and it seems like it's working, but even software, you know, there is always bug shows up later. The same thing happens in the complex hardware. The bug show up while you are using in the field, then you're in trouble. So how do you know this chip created is compliant with what you intended to do? This is a very complex problem. It's not that easy to answer. Actually, some theory said it's impossible to test every cases. It's just you have to live with a certain percentage of possibility of having a bug in the chip. Okay, so it's not the clean cut things. You design the large semiconductor chip. Well, wow, very happy, finally finished, and it seemed to be working. It's doing all the instructions, so and so. But certain data shows up once in a blue moon, then answer is wrong. Okay? And yeah, it's the FPG. We created 100 CPU, 20 of them shows wrong, kind of case happen, right? Well, when you go through this standard cell approach, we created 1 million chip. It's about 500 chips is wrong. How do you detect that? You have to screen out, but screen out is not easy. So this is testing engineer. We need a testing engineer for this purpose. And the test engineers create the optimum test pattern to test it out. So, okay. So that's all for today, and I hope you enjoyed, and if you like it, please click subscribe and like, and wait for the next video.